Welcome to Lesson 10A, Clean Rooms. We're going to talk about clean rooms, a special case of this room ventilation that we've been talking about. By introduction, the major distinction between a clean room and a regular ventilation is that general ventilation is designed to protect the occupants. So in other words, we want to keep the chemicals below the PEL and keep particles low and keep viruses and stuff out of the building. This is also true with local ventilation, and we'll talk about that later, but basically that's hoods. Whereas with a clean room, we obviously care about the occupants, but the major goal is to protect a product. This is often used in the electronics industry, and typically we're looking at particles. You care about gases too, but usually it's particles that are a problem. You get dust particles that can settle on electronic wafers and things like that. These can damage product you're trying to make. It turns out that clean rooms have very, very small number of particles per cubic meter. In other words, the clean room requirements are pretty strict in terms of things like temperature. Usually they're pretty cool rooms. Humidity, usually very low humidity because you don't want water condensing on your electronic products either. Also things you might not think about like static electricity. You don't want sparks that can ruin things that you're doing, especially important for electronics. Concentration levels, of course, like we've been talking about, and this includes vapors and particles. In fact, clean rooms are classified by particles. There are various configurations. Since we're talking about particles, you've probably heard of these, especially now with some of the masks with COVID. HEPA filters and ULPA filters. Clean rooms often use very high efficiency cleaners. We're talking about clean rooms. There's different kinds, vertical flow coming down from the ceiling, that little pores in the floor that go and then come up, and there's a big cleaner up here like that. You can have the same kind of thing except horizontal flow. You can have different kinds of vertical flow down, but it goes out the sides instead of through the floor. These first three are kind of like a displacement ventilation that we talked about before, except the flow is coming from top to bottom instead of the other way. These are usually applications where you're trying to keep the particles from getting into the air in the first place. You try to force them to settle faster. That's why they usually come from the top. You can also have benches. This D is a kind of a tabletop bench, and you have the air coming from the ceiling, but then you have additional air from the room going into this system that pushes it down, and you're going to work in this area here. And then here's some kind of isolated ones where you have an island. You just have the ventilation right over the island. It's kind of the opposite of a hood. Instead of drawing air out through a hood, you have air blowing down onto your workpiece. Of course, people wear white lab coats, and sometimes they put plastics over their shoes and gloves and all that to keep particles from coming off people. And then here's an application where it's just a workstation. The ventilation system itself, you can have these different configurations, but basically it's the same as what we've been talking about. You have some kind of room, incoming air, outgoing air, so there's a QS, a supply air, and it goes through a filter of some sort, and there's some makeup air that's not shown here that comes from outside. They try to keep that at a minimum. As I said, clean rooms are classified by particles. This gets a little complicated, so let me just explain. Originally, there was no metric, there were just English. So you have this class 1 in English units. What we do is we use this column. The DP 0.5 micron is the one that we use to base these clean room classifications on. So an English class 1 clean room, and I put these in blue then, is 1 particle per cubic foot. That is really, really clean. There aren't very many class 1 clean rooms, but that's what that means. And then 10 means 10 particles per cubic foot. This little symbol, usually for number, is an abbreviation for particles or number of particles. You had 1, 10, 100, etc. for various classes. Then metric units came in, and so they defined M1, the same kind of thing except it's 10 to the 1 instead of actual number. 10 to the 1 particles per meter cubed, and then M2 would be 10 to the 2 particles per meter cubed, or 100. So it's still kind of a log-looking scale every decade. So that's what they did. And then if you have a class 1 clean room and you want to do things in metric, Then they introduced this other intermediate values, M1.5, M2.5, and those are kind of just a way of saying, I have a class 1 clean room, but in metric units, this turns out to be 35.3 particles per meter cubed instead of 1 particle per foot cubed. Both English and SI classes are based on 0.5 micron particles. If you're dealing with particles that are 0.2 microns, you would use this column here, 0.2 microns and larger. Well, you have to meet these criteria. So to have a class 10, you have to have 75 particles per cubic foot or less in order to be classified as a class 10. The conversion meter cubed per foot cubed is 0.3048 meters per foot, and then we cube that. So the conversion is equal to 0.02832 meter cube per foot cube. So that's a unity conversion factor. Or if you're going the other way, 35.31 feet cubed per meter cubed. And that's why we see these numbers here. By the way, these concentrations, number per meter cubed or number per foot cubed, are called number concentrations. We had mass concentrations, we had molar concentrations. For particles, you can still use mass concentrations when you're talking about particles. We use instead number concentration, the number of particles per cubic foot or per cubic meter. Now, if we take this table and plot these data is a plural word, so plot these data, and we're going to use a log plot. We have dp in microns on the horizontal axis, and that's a log scale. And then we have C number. These are number concentrations, which we call C number. So if we plot those data, again, it's based on 0.5 microns. That's the special location on this scale. 1 particle per cubic foot is class 1. Well, that's how we defined class 1. Class 10 is 10 particles per cubic feet, etc. The metric ones fall in between. It turns out that class M2 is kind of halfway in between there. If you just look at these numbers, M2 is here between class 1 and class 10. So you can kind of fill those in. These are all straight lines, so you can extrapolate as needed. The circles are only from the table, but you can easily extrapolate all these guys to wherever you want. Another comment, the smaller the class is short for classification, the cleaner the air. So if you're bragging about your clean room, you say, I have a class 10 clean room, and then someone else says, well, I have a class 100 clean room. Well, he's off kilter there because a class 10 is better than a class 100. How to use this plot, it's really the same as the table, but sometimes you have to extrapolate. I'll just do a quick example. Suppose I have C number equal 20 particles per cubic foot, and that's the best that I can do in my clean room. dP, by the way, is particle diameter. So we're talking about, say, particles that are greater than or equal to 2.0 microns. And so what class is this clean room? Well, I can go up to this diagram and say I have 2 micron particles here, and I go straight up and I have 20 particles per cubic foot. That's this little tick. This is an English system. And you come over and you say, here I am. So what class is it? Well, it's not good enough to be a class 100, which is this line. It is definitely good enough to be a class 1000. It's kind of almost exactly in between. We would say it's a class 1000 clean room in English units. Let me do an example. As I said, the actual ventilation system doesn't have to be different, but in this case, we'll do an example where it is different. We had 1 air cleaner, but now suppose we have 2 air cleaners, and that's sometimes the case with a clean room. So here's our room. We have negligible infiltration and exfiltration, which is often the case in these clean rooms because they're tightly sealed up other than the forced air ventilation system. So we have a source, we have some wall losses. I always draw it to the side, but these are typically particles falling from the air onto some surfaces, so you get rid of some particles that way. We have 2 air cleaners, 1 coming in from the outside air. The outside air is dirty. There's a lot of particles in the outside air here. It's about 1,000 particles per cubic meter. We go through an air cleaner before we even come into the room, the makeup air. We also have an air cleaner in this loop to clean the recirculated air. We have an F, a makeup air fraction, just like we had before, and a fan, of course, blowing things through. Here's the specifications. We have 98% efficiency air cleaners for both of them. 5% makeup air, so that's pretty small compared to buildings typically, but we don't want a lot of makeup air because we have to spend a lot of money cleaning it. There's a lot of pressure drop through here, so you have to have big fans. So we try to do as little as we can so that we can get fresh air enough for the people to have fresh air, but we don't want to have to pay to clean it. The number of particles in the ambient air is given. dP is the particle size of concern. So we're going to be looking at 1 micron, which is not on here. So in this case, we're going to have to do some interpolation between these guys. That's where this plot comes in handy because you can actually do better than interpolation. You can figure out the actual numbers by doing those straight lines. And then we have a supply ventilation rate, QS. We have a source in particles per minute. The volume of the room, ASKW, those are the same as before. C naught is the initial particle concentration in the room. So what we want to do in this case is find what class of clean room is this and calculate how long it'll take to achieve these classes. The first solution, since we did not look at this kind of exact configuration yet, is to calculate the CSS. First, you have to do a contaminant mass balance. You have to look at the cleaners. You know how to analyze flow across cleaners. You know how to analyze rooms with recirculation. You know how to include wall losses and sources in a well-mixed room, makeup air. Calculate C2 here coming through that cleaner and CS that's coming through both. You have to understand how to do T's. I'm not going to do this. I give you the answer. Do this on your own for practice. You have to be able to examine a ventilation schematic like this one and generate an equation for CSS. So let's just plug in the numbers here. CSS equal our source. These are now particles per minute plus QS times CA, 1,000 particles per cubic meter, F1 minus eta 2, and then we have to put in the denominator. And when you plug into your calculator, you get C number, steady state, is equal to 10.67 particles per meter cubed. So the best that we can achieve with this particular ventilation is a little bit greater than 10 particles per cubic meter. Use our conversion, this turns out to be 0.302 particles per cubic foot. Looking at our plot, 1 micron here is our particles of interest. We can extrapolate these as needed, as I've said. So now, where are we on this? We are at 0.302 particles per cubic foot. That's the best we can do with this ventilation system with all of these parameters that I have. 0.302 is about here. If you go straight across, you can see that we're at this point right here, which is above the class 1. We'd have to achieve this point, 0.21. We're here for these 1 micron particles. So we can see that we cannot achieve a class 1. Numerically, at 1 micron, class 1 requires 0.21 particles per cubic foot, 7.40 particles per cubic meter. And we have 10.7 particles per cubic meter. So you can see that we cannot achieve a class 1 with this particular ventilation system. But a class 10 requires, since these are log scales, once you do this interpolation and you get 7.4, you just multiply by 10. So 74 particles per cubic meter, and we have 10.7 particles per cubic meter. So we can achieve class 10. So I would call this a class 10 clean room in terms of the English system. At 1 micron, a class 100 would require 740 particles per meter cubed. So we can definitely call this a class 10 clean room. Then the second part of the problem, I asked, how long will it take to achieve class 10,000, 1,100, etc.? So how long? Well, recall when we have our standard form dC dt equal B minus AT, by the way, you need to generate A and B in order to generate this equation, so that'll be part of your exercise. I want you all to do this on your own.
Dude, is that like a homework assignment, man?
No, Joe, but it's for your own good.
Bummer, dude.
A will be this denominator divided by V, volume, and the B will be this numerator divided by volume. So we have A, and if you recall, once you have it in standard form, T equal -1 over that coefficient A, natural log of CSS minus C at some time over CSS minus C at time 0. That's the equation we use. How long will it take to get there? This is valid for any ventilation system or flux chamber as long as you have constant A and B coefficients, which we do in this case because nothing's fluctuating. C is the only thing changing. It turns out, you plug in this denominator and divide by the volume of the room, that's your A. That A turns out to be 0.099933, 1 over minute. And so you have T equal -1 over that A. Natural log 10.67 minus 74. This is for class 10 divided by 10.67 minus 10 to the 5th. Our initial value was 10 to the 5th. That was given. 74 is what we're shooting for. That'll be our C of T to get a class 10. And then 10.67 was the steady state value if you let this run forever. And this gives me 73.7 minutes, or approximately 74 minutes. That's good. I mean, in a little over an hour, you can achieve your class 10, so that's not too bad. For class 100, you just repeat, do everything except use 740 instead of 74 as our C at T, and you end up with T equal 49 minutes. These are just the 2 digits. If you repeat this, at class 10 and class 100, we had 74 and 49 respectively. If you keep doing this class 1000, it takes you 26 minutes. To get class 10,000, which is a pretty crappy clean room, it only takes you 3 minutes. What about class 1? Well, if you plug this in your calculator, you're going to get not a number or something like that. Your calculator is going to flash at you. In other words, this is infinity. And we've already said that this is not possible. You can never achieve a class 1, so that's why we call this a class 10. Time to achieve a better class, better meaning a smaller number, keeps increasing as you go to smaller numbers, smaller classes, which means better classes. And then you get to a point where you cannot achieve it. That's why we could not call this a class 1, but we can call it a class 10.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.